The purpose of this lab is to explore Newton's second law of motion when the net force on the system is zero. This is done by observing an object in constant motion in a single direction, creating a computer model of the object by using the average velocity of the object, and comparing the graphs of position versus time of both. In order to simulate an object moving in constant motion, I decided to film an apple with diameter of about 8.9 centimeters and mass of 0.2 kilograms, moving across a dining hall conveyor belt. Using Tracker, I set the origin of the axes as the center of the apple, created a length scale by placing the calibration stick over the diameter of the apple and specifying the length, and had the apple move in the positive x direction of the axis, as seen. I then, frame by frame, tracked the center of the apple during the approximately 2 seconds of motion using points that captured the object's position. As you can see, Tracker created a time versus position graph from these points and a table showing the x and y components of the object in relation to time. If I had made the y-axis the horizontal direction and the x-axis the vertical direction, the graph would have remained the same shape, except that the y-axis would be labeled with y, and the table would have y coordinates increasing instead of the x coordinates increasing. Note that although there is some movement in the y direction of the object, it is very negligible, and instead we can focus solely on the movement in the x direction. In order to create an accurate computer model of the object, I had to assume that the velocity of the object remained constant throughout the interval of motion. Based on this assumption, I took the initial position of the first 2 points in Tracker, subtracted them, and divided by the change in time to calculate the velocity of the whole interval, neglecting the velocity in the y direction. However, that did not create an accurate representation of the object's true motion, which will be seen later in this video. So I then calculated the velocity of the object using the final and initial points of the graph, as can be seen here. With this information, I coded a model for the apple's motion in VPython. I set the object's initial velocity based on the calculation I made in the final and initial positions of the apple. Though I included the mass, this is negligible, as I will show later in the video. I then set a calculation loop to emulate Newton's second law of motion, setting the net force equal to 0, and coding for the changes in position and velocity as time changed. The result of the model is as follows. Finally, I put the position versus time graphs together in a Google spreadsheet with the red solid line representing the model's motion and the blue dotted line as the object's observed motion. As you can see, the lines are very similar to each other. But near the beginning, however, the velocity of the object observed near the beginning of the time period, however, the velocity of the object, as can be seen by the slope, is clearly less than that of the model, probably due to my shaking of the camera in an effort to get into position to film. Because I had initially used the first 2 points of the object's motion in the calculation for velocity, my initial model's line was way under that of the object's observed line, forcing me to reevaluate the velocity. Throughout the rest of the interval, both lines remained fairly parallel, except at the end, where I probably shook my camera in my effort to save the apple from being wasted. In conclusion, this lab allows us to understand Newton's second law as shown here when the net force on the object is 0, which can be otherwise supported by Newton's first law. Notice how the law mentions net force. Though it is often not possible to know all the forces acting on the system, we can apply this law if all the forces add up to 0. In the case of the apple, we know that gravity, air resistance, and friction are all acting upon it, but the net force is still 0, satisfying this requirement. Since the net force is 0, the mass of the object is negligible in this case because the whole term on the left is 0 regardless of what it is. Thus, the change in velocity over the change in time otherwise known as acceleration, is zero, meaning that the object will have a constant velocity and, as Newton's first law states, will remain in motion until acted upon by another external force. Thanks for watching.